Welcome back. In the previous two lessons, you learned about a data structure called the stack. In the next two lessons, you'll learn about a new data structure called the queue. In this lesson, you'll find out what a queue is, how the main queue operations happen, evaluate the queue in comparison to other data structures, and think about ways that queues are used in the design of computer systems. Like the stack and the array, a queue is a linear data structure. It's implemented in an array. It has two pointers called the head and the tail. Sometimes people use front and back. I'm going to use head and tail. The head pointer points to the first value in the queue, and the tail pointer points to the final end value in the queue. A queue works like a queue in real life. For example, if you're queuing up at a cafe to order some food. When new data is added, it joins the end of the queue, just as you would join the end of the queue if you came into a canteen and there was a queue. You would go to the end of the queue. But data leaves the queue at the front. Just as in a canteen, the person at the front of the queue would be the one to be served next. Adding data at the back of the queue is called enqueuing, and taking data from the front of the queue is called dequeuing. These are the only two operations you can carry out with a queue. So let's draw a queue and see what happens to it as we carry out these four commands. To enqueue the letter A, to enqueue the letter B, to dequeue a value, and then add X to the queue. So adding A and B, taking a value away, and then adding X. Here's an empty queue. As you can see, there are two pointers called tail and head. We're going to enqueue the letter A. Remember that when we enqueue, we add data at the tail of the queue. So let's do that now. We add data at the tail of the queue, and then the tail moves up by 1. A has now been added to the queue. Now let's enqueue another value, B. Enqueue adds values at the tail, so B is added at the tail pointer. And the tail pointer moves along by 1 to show the new tail of the queue. Now let's see what happens when we dequeue. When we dequeue, we remove a value from the head of the queue. In this case, the value A. The value would be returned or output by the dequeue function. The head now moves up the queue by 1. I've shown the value A disappearing, but strictly speaking, the computer doesn't even bother to delete the value. It's just that because it's no longer got a pointer to that value, it's as if the value no longer exists. And then finally, we'll add a further value to the queue, in this case, the letter X. So let's see what happens when we enqueue X to the queue. X is added at the tail, and the tail moves up by 1. So enqueue happens at the back of the queue where the tail is, and dequeue happens at the front where the head is. Let's go through that entire process to see the queue in action. Enqueue A, enqueue B, dequeue and return that value, and then enqueue X. We call the queue a FIFO or FIFO data structure. That stands for first in, first out. The item that has been in the queue for longest is the first one to go. So the first person to add, so the first person to join a queue is the first person who is served when the canteen opens. And a queue inside the computer works in the same way. Whatever data has been waiting for longest in the queue will be the first one to be output from the queue. So there are quite a lot of uses for this data structure inside the computer, and a very common one that you'll be familiar with probably is a print queue. So if several different people send their work to the same printer to be printed out, those jobs will go into a queue, and the one that's been waiting longest will be the first to be printed out on the printer. Unlike a stack, a queue preserves the order of the data. As you will remember, a stack reverses the order of the data, and a queue keeps the data in the same order that it joined the queue. Advantages of the queue compared, let's say, to other data structures such as lists and arrays is that there are only 2 points of access, one where we add data and one where we take it away. That means that all operations are of constant big O value, big O of 1. It takes one action to add or remove from a queue. There's no wasted space because the data is just stored, joined up contiguously in the array. And the order of the items is retained. That is, the computer remembers what order the data items have been added, and it keeps that order. And if you want that, for example with a print queue, then this is the ideal data structure. Of course, like the stack, there are limitations. We can't do a lot of actions with a queue. We can't traverse a queue. All we can do is just dequeue all the items one after the other. We can't edit, we can't insert data into the middle of a queue. There is another thing as well, because as you add and take away items from the queue, the pointers move up the queue, always up. They never come back down again. So eventually you're going to reach the end of the array. There are ways around this. We'll look at those in a minute. So let's just summarize. Here are my list of operations that we can do with data structures. And really, there are only 2 we can do with a queue, enqueue and dequeue. However, we could also write some additional functions to check if the queue is full up or empty. We'll look at those in a couple of minutes. So I spoke earlier about the problem with a queue, which is that it's always moving in one direction. So I've got a queue that's got ABC in it, and let's add a few values and take a few away. And so we're using the queue in the normal day-to-day way that we would use a queue, taking away at one end and adding at the other end. And look what's happened. We've reached the end of the array. There is still space, but it's lost space. It's off the end of the queue. And so we've hit the end of the available space. And this will inevitably happen with a queue because the tail and the head only move in one direction along the array, and so they're bound eventually to reach the limit of the available space. However, there is a solution to this, and what people do is they start using the other end of the array as the front of the queue. So we can imagine that the queue is effectively looped round, and we're adding values at the beginning again. And this means that the queue, if we treat a queue like this as a loop, and we go back to the start again, That means we don't hit an end point. Of course, you can eventually fill up all available spaces, and at this point you can't add any more to the queue. So obviously there is some kind of limit to how many values you can add to the queue. Okay, so you should know what a queue is, and you should know what the two queue operations are. Just to remind you, they're enqueue and dequeue, and enqueue happens at the tail and dequeue happens at the head. You should have an idea of why we use queues. They're not perfect. There's a lot of things we can't do with queues, but they're very useful in some cases. For example, in a print queue. And I'm going to leave you with a quick test about the queue. So see if you can answer these. Ideally, write the answers down on paper. And you'll find the answers earlier on in the lesson, so you can rewind and have a look at that. Explain why a queue is efficient in time, quick to use, and efficient in space, doesn't waste a lot of space. Explain what the disadvantages are. Give a real life example where you would use a queue data structure and say why it's so useful. And draw a queue and show 3 or 4 operations that you can do with the queue and how the queue itself will change as those operations occur. Okay, so next lesson we're going to look at programming a queue in Python. So see you then. Bye for now.